Welcome to The Explainer. I am absolutely thrilled to have you here today. Now, if you've ever walked past a massive construction site, you've definitely seen them, right? Those towering, intricate webs of steel just hugging the sides of skyscrapers? Scaffolding is literally the temporary highway in the sky that makes modern construction even possible. But today, we're not just looking at how these structures are built. No, we are going to conduct a fascinating spatial autopsy of exactly how these massive steel structures fail. Let's dive right in.
Think about this for a second. It takes weeks of painstaking labor to erect a high-rise scaffolding system, mapping thousands of individual steel components into this perfectly rigid grid. But it takes less than 3 seconds for that entire grid to completely collapse into the street. 3 seconds. That terrifying speed? That's not a fluke. Actually, we really need to reframe these events. They aren't unpredictable accidents. There are highly predictable breaches of engineering limits. A scaffolding collapse follows a very specific sequence of mechanical stress, and today we're going to break down exactly how that happens.
To really understand why this happens, we have to start our autopsy exactly where gravity tells us to, down in the dirt. Most people naturally look up at scaffolding, but the truth is, the absolutely most critical part of the entire system is sitting right beneath your feet.
Check out the brilliant simplicity of proper load management here. See that metal baseplate resting on a wide wooden board? That's called a mudsill. OSHA Rule 1926.451 strictly requires these firm foundations, and for good reason. Scaffolding generates an immense amount of downward force. That mudsill's entire job is to take all that concentrated weight of the steel, the workers, the heavy materials, and evenly spread it right across the soil. It helps to think of a scaffold not as a static, dead object, but as a living channel for gravity. Let's trace that visual path. The weight starts way up at the working platform. Gravity then demands that the weight travels securely down through those vertical legs. We call those standards. From there, it hits the base plates, and finally, it's safely dispersed into firm soil. Every single ounce of weight has to travel this exact load path. So, the absolutely crucial question is, what happens when we interrupt that path? Well, it's a pretty simple, devastating equation. Soft ground equals base plate sinkage, which equals structural collapse. If a builder swaps out a proper mudsill for, say, some scrap wood, or builds on soft, muddy ground after a rainstorm, physics breaks down. Just a single leg sinks, and that tiny fraction of an inch of settling at the base creates this massive point load that overstresses the couplers and tilts the entire vertical column above it. Basically, a failure at the foundation instantly fractures the integrity of every single level above it. All right, moving higher up the structure, we run into a whole new set of problems. You see, gravity is no longer our only enemy once we leave the ground. Now we have to confront lateral or sideways forces. And that brings us to the golden rule of scaffolding stability, the 4-to-1 ratio. This is a very strict OSHA specification. A scaffold's height can only safely go 4 times its base width before it turns into a highly dangerous freestanding lever. So if you have a 5-foot wide base, you can safely build up to 20 feet. But the very moment you cross that threshold, the entire structure becomes mathematically unstable on its own. To fight back against this, builders use strict mathematical tying intervals. Basically, to stop the scaffold from acting like a giant freestanding lever, they have to physically lock the structure into the adjacent building. They've got to guy, tie, or brace it right at that 4-to-1 limit. And it doesn't stop there. They have to keep tying it vertically every 20 to 26 feet and horizontally every 30 feet. These ties are literally the anchors that tame those lateral forces, constantly trying to pull the scaffold away from the wall. Now you might be wondering, why are those lateral forces so dangerous in the first place? Well, it mostly comes down to what we call the sail effect. On high-rise projects, builders are understandably required to use dense safety netting to catch falling debris. But unpredictable weather can instantly turn that safety netting into a massive sail. It catches heavy wind gusts, exponentially multiplying the lateral push that's tearing at the steel frame. So those mathematical tie-offs we just talked about, they are literally the only thing keeping the mass intact against a 40-mile-per-hour gust of wind. Okay, so let's look at internal stability. Because even when it's securely tied to a building, a scaffold still has to resist the internal swaying caused by wind or just the shifting weight of a crew moving across the platforms. Enter cross-bracing. These diagonal steel tubes form an X shape right between the frames, which creates a highly rigid triangular support effect. Triangles are structurally incredibly strong. These cross braces act as the literal spine of the scaffold. They distribute the loads evenly across the whole system and add the absolutely crucial stiffness needed to prevent the steel from bending or twisting under pressure. Picture this in your head, or take a look at how this animates out. On one side, we have a perfectly rigid rectangle. With the diagonal bracing in place, all the right angles are safely locked. The scaffold is stiff and secure. But what happens if you remove just one single diagonal brace? Instantly, you lose all lateral stability. That safe, rigid rectangle violently shifts into a collapsing parallelogram. It twists, it peels away from the building, and the whole thing comes down.
So that brings us to a really important transition, the human element. If these structures are so perfectly calculated, why are they so often compromised on actual job sites? Well, it all comes down to what we call the modification trap.
I want to pose this critical question to you. What actually happens when you remove a single wall tie? On a busy construction site, workers are under immense schedule pressure. A pipe might be in the way, or maybe they need to swing a material crane in. It becomes incredibly tempting to just unscrew one little tie back or remove one cross brace just to get the job done a bit faster.
Let's look at a pretty tragic real-world example of this from June 2019 in Brooklyn. This was a 12-story site entirely shrouded in safety netting, meaning that sail effect we talked about was in full force. A stucco worker, needing to fill some holes in the wall, just disconnected the critical scaffold tiebacks. The superintendent actually warned the scaffolding foreman to dismantle the now unsecured frame, but that warning was completely ignored, and the result? A total, catastrophic structural failure. As an engineer evaluating these sites, I have to give you a bit of a reality check here. It's simple. If you remove one part, the entire structural calculation for that bay is void. A scaffold isn't just a physical highway made of steel. It's a highly fragile mathematical equation. You change a single variable without an engineer's approval, and the entire equation collapses. And that equation breaks terrifyingly easily. Notice these decoupled vertical legs here? That is the direct result of the dangerous omission of a simple locking pin. It's an almost invisible flaw that workers naturally normalize over time. They think, hey, it's just one pin. But this is exactly why OSHA mandates a designated competent person, someone who actually understands the structural logic, to inspect the scaffolding for these exact kinds of defects before every single work shift. Look, I totally get it. We really have to acknowledge the real tension on job sites between project deadlines and safety. But the perceived speed of unauthorized modifications, like popping off a brace to make room for a crane, is a deadly illusion. The actual consequence of ignoring structural logic doesn't save any time at all. It guarantees absolute project destruction. A collapse completely obliterates the budget, halts the timeline for months, ruins a firm's reputation, and most tragically of all, it takes human lives. So how do we prevent this? Structural engineers and site supervisors rely on rigorous daily discipline. Here is a highly practical quick check that should be performed religiously on site. Are all base plates on firm, level mud sills and definitely not scrap wood? Is that 4-to-1 height-to-base ratio strictly maintained? Are there sufficient ties locking the system securely to the building? Are the access ladders actually secured so workers aren't using the cross braces as makeshift stairs? And finally, are the platforms fully decked with no gaps wider than 1 inch, so tools don't just fall right through to the ground below? I want to leave you with this provocative thought as we wrap up today's explainer. When you are standing 10 stories up on a thin steel plank, is safety oversight just some annoying bureaucratic delay, or is it literally the only math keeping your structure standing against the wind? Respecting the rules of physics and trusting the engineering calculations is absolutely the only way to survive the highway in the sky. Thank you so much for joining me today, and keep looking up.